So let's continue the uh, intrinsic self-healing. So one of the equations that we derived at the end is that is this equation that relates fracture toughness to critical energy release rate. And for a given time, if you keep the time constant, uh, the healing is proportional to square root of delta x squared, which means it's proportional to a square root of d. D is the basically diffusion constant. Now, if I can quickly share with you my notes to remind you of this equation here. And so what you can see there is that one way to make this diffusion faster is to increase the temperature, okay? For a given, this is for a given activation energy that is here. Okay, but in some cases, like if I have a thermoplastic polymer and I just don't make any changes in the microstructure, then obviously the activation energy is not going to change. So that means I only have one variable to expedite this healing, and that is increasing the temperature. But in some other cases, we can do other things. An example I want to share with you, it's not exactly in the context of self-healing, but it shows the changes we can do to the activation energy itself. If you go back to the slides, and as soon as I find my okay, I found my mouse. I don't know why this this is an example of, this is a polymer fiber that was hollow, that had some pores in it. Now, why we made those holes in everything is a separate subject. But if you look on the surface of this guy, after we coated the polymer, the fiber, the boundaries of the initial fiber is here that I'm showing you. If I when I coat it with another polymer, PMMA in this case, on the surface you see holes like this. Now, in a typical self-healing experiment, holes come because of some propagation of, as a result of the failure, as a result of excessive load. The reason pores appeared here is a different subject. Regardless, cracks. The reason cracks appear here is a different subject, but at least cracks are there. So these are crack-like openings. And in this particular case, we could not increase the temp. We wanted to close these cracks. So basically, our goal was to close these cracks that I'm showing you. But we could not increase that. I've zoomed in here so that you can see the cracks even better. But we could not increase the temperature of the material, because if we had increased the temperature of the material, the base, the core that is here, that I'm showing you here, and these walls of the core would have melted prior to these cracks healing. So basically now, if you go back to the diffusion equation, my goal is to reduce this, accelerate the diffusion. So delta X is higher, which means I need to have a higher diffusion coefficient of the higher, faster diffusion. But then if you look here, I only have two parameters, the activation energy and the temperature here. And we said that a temperature in this case is a no-no. We cannot increase the temperature. So basically, we are left with one choice, which is reducing the activation energy, which would have the same effect of increasing the temperature. And the way we did it is, in some sense, if you go back to the literature of shape memory polymers, the mechanism, and if you look at the part we talked about, the effect of moisture, that moisture can go in between polymer chains and reduce the activation energy, like act as a lubricant, allow chains to move faster. That's exactly what we did. Basically, we put the fiber, this was our fiber that I'm showing you with these stars, or maybe these arrows. I'm showing with this arrow here. And we put it in a chamber and subjected it to, inside this chamber, there's a vapor of a solvent. And so vapor of PMMA solvent, in this case, was dimethyl formamide. Now, when you do that, something very interesting happens. Basically, these DMF molecules go in between polymer chains, act as a lubricant, allow them to move faster over one another. And so, so basically, this is before. And for instance, you see all these roughnesses and things that appear like cracks. And when you look at the modified polymer, after treatment with DMF, you see that this is actually much, much smoother. So in this case, what has happened is, actually, if I go one slide back, is that we did not change the temperature. This guy remained constant, and what changed was the activation energy. We reduced the activation energy. So all I'm saying is that in some cases, if you're limited by temperature, you cannot increase the temperature because something else is in your system that will be degraded or loses its form, then you can do this. Another option to trigger intrinsic self-healing is to use polymers that can interact with each other with reformable or reversible reactions, with reformable bonds or reversible reactions. Typically, there's a fancy name for these chunk of molecules that's called the supramolecule assembly. It's a group of molecules, basically. All the atoms within each molecule are connected to each other with covalent bonds, but the interaction between them is with bonds that can break, but if you put the two pieces together at the same temperature, they can reform. An example of that is hydrogen bonds, basically some form of non-covalent bonds. These are reactions that have very low activation energy. So for instance, if you look at this figure, they broke the two parts with a razor blade. They put the two parts together, and then they pulled on them, and it has become one again. And so basically, the hydrogen bonds between chains reform here in this step. Now, these are reformable bonds or reversible reactions, but it means they're not very strong. So you cannot make an airplane out of them because they're very soft. But if load bearing is not your primary concern, then they're not a bad solution. So now, I hope one thing you get from everything I said so far is that the scope of applying intrinsic self-healing is limited. There are certain materials that show this behavior, such as thermoplastics, that you heat them up, they diffuse, and they basically they heal the cracks, or it's based on cases that we can reduce the activation energy, or it's based on cases that the activation energy is very low to begin with, as a result of which often these materials, those that are based on low activation energy, are very weak. And so that's why people have started looking at extrinsic self-healing, and I will start that in the next video.